I thought it would be a good idea to return to abiogenesis. So remember, that just says, or abiogenesis is an idea about the origin of life, how life started on Earth. The idea is that you just need the right ingredients to have life, and of course the right conditions. And with those, life should form spontaneously. Now there was a famous experiment done by Urey and Miller. It's often called the Urey-Miller experiment or the Miller-Urey experiment. Now, it's a bit controversial, but I want to explain a little bit more about it, just so you can sort of think a little bit about it and if it really showed anything interesting. I think it was interesting, but I don't know what we can really take from the results exactly. So, well, let's just see what they did here. The idea was they tried to take the early ingredients. This was the idea here. They tried to use, what they thought at the time. They tried to say, okay, well, when did life start on Earth? Okay, about 3.5 to 3.8 billion years ago. What kind of ingredients were there on Earth at that time? So they put those early ingredients in a jar. Basically, they added sparks, and they basically let it go. So in this experiment right here, you end up with something kind of cool. With just those basic starts, you end up with amino acids. Now, amino acids don't necessarily mean that something is alive. In fact, there's a big jump missing here. So this is the whole thing that where we're sort of missing something here. We're sort of missing this, next leap right here, and say, does that somehow lead to life? There's a big piece missing here, of course. I mean, anything that's alive has amino acids in it, but there are lots of things that are not alive that also have amino acids. So it doesn't necessarily mean, if you just take the early ingredients on Earth, you add some sparks, and you get amino acids, it doesn't necessarily mean it gives you life. But it is still really interesting. Now, there is a whole step obviously missing here. I mean, maybe you'd have to leave these amino acids for a few billion years and then see if they really end up forming life. It's a little bit difficult to prove this. So there is this piece missing here. But these amino acids here that you get, it turns out there's two types of amino acids. They're sort of left-handed and right-handed. We say that they're chiral or chirality. So what we mean by that is that amino acids, they come in certain forms. It's like there's mirror images of each other. So there can be left and right sort of sided ones. And the weird issue is that all life on Earth, everything that's alive, is left-handed amino acids only. And yet, in this experiment here, you only get, in this experiment here, you don't get only left-handed, you get left and right-handed amino acids together. So what does that tell us? We're not quite sure. We just know that there's obviously a problem here. Now, some people have said, oh, well, the fact that we have only left-handed amino acids is evidence of common ancestry. In other words, that all of us come from the same organism. Now, this is a very controversial subject. I mean, this is something that there's a huge amount of debate between evolutionists and creationists, as they're often sort of coarsely labeled. Each of them finds problems with the other's ideas and interpretations, so I'm not going to really get into there. If you do some YouTube videos about common ancestry, you'll see a huge amount of people saying this is complete utter garbage, this is totally wrong. And then if you go to videos, obviously, about creationism, you'll see the same thing. So this is very, very controversial, but I think it's still interesting to know about it and know what these people did and what they were trying to show. Now, there are some other problems. One other problem is that now we know that the ingredients that they assumed then, on Earth at the time, are actually now thought to be wrong. In other words, they weren't representative of Earth's early atmosphere. So new experiments with better data and ingredients, they're not actually that helpful. The reason is that we have problems with knowing what the early Earth was like. In other words, we don't really know the early Earth ingredients that well. There's a lot of debate, for example, about hydrogen gas. So was there any? If so, how much? Turns out that makes a big difference. So there obviously are some problems with using this, but still a very interesting experiment, I think. So it's just a matter then of trying to do this and trying to see if they give us something. We're still missing this step, though, of, once you get amino acids, how do you get from there to life? We still don't know. Now, there are some experiments that have been done that I think they're sort of related to abiogenesis in a sense. One of them was a NASA experiment, or NASA mission called Stardust. Now, this one was really cool. What they did, they launched it in 1999. Maybe I'll write that down. So they actually launched this in 1999, and what it did, it actually followed a comet. So this little spacecraft actually followed a comet. I think it was called Comet Wild 2. Maybe I'll write that down. There we go. This is worth looking up. It's really interesting. So it essentially followed a comet, and a comet is just a bunch of rock and ice. And these pieces, it would, of course, as it comes close to the sun, some of the ice melts, so little bits of sort of comet material would sort of fly behind it. And so this thing essentially was trying to catch some of that material. So it was trying to take the material from a comet and then bring it back to Earth. So it returned to Earth in 2006. And this is apparently the lander here. That's what NASA said, at least. So this here is a little piece that landed back on Earth. So it's really interesting then. They took this inside, of course. It was all sealed up. They took it in a lab, and they could take a look at the materials in there. And what's really interesting is that there were amino acids found in this comet. So in other words, this comet also contains the basic building blocks that we're made of. So that, I think, is really interesting, that the things that we're made of are also found in comets. Now, does that mean that we all have the same materials and you just need the right conditions? Not necessarily, but this certainly still means that abiogenesis is possible. Another really neat experiment is called Rosetta, and that's by the European Space Agency. Now, this one is still active. It was actually launched in 2004, and what it's supposed to do, it's supposed to actually land on a comet. So this one here is actually going to land on one. So this is so cool. So what this is, and it's actually on its way right now. I think it's supposed to land in 2014. So it's supposed to land on a comet. So the idea is this: it's going to get close enough to this comet right here, and what it's going to do then is take a little grappling hook, basically hook itself onto there, and then take some readings and find out, what are comets really made of. So we'll see what they find. But I think an interesting question is, why comets? Why are we so interested in those? Well, remember from previous videos that there's strong evidence that comets hit the Earth, the early Earth. We call that the late heavy bombardment. Basically, right after the Earth was formed, or not long after that, there were lots of impacts and things like that. A little bit later on, there was a lot more. So this here is what we call the late heavy bombardment. And we think that those likely gave us our water. Because remember, on the Earth at the time, they would have been all molten and hot. So it would have been probably too hot for water. And yet we have water. So we think our water came from lots and lots of these comets slamming into the Earth. So that's why we're so interested in comets, because these might have seeded the Earth with its primordial material that you need to make life. So maybe it also gave us the amino acids that go through some unknown process that we don't know exactly and led to life. So what conclusions can we make from these? How does this help our search for life? Well, it doesn't necessarily give us so much information, although there's certainly a lot to be gained, and that's why I think these missions are really important. But maybe the building blocks for life are all around us, and on other planets too. So with the right conditions, perhaps life can start spontaneously. In other words, perhaps abiogenesis is how life started on Earth. So what we should do now is return to panspermia, which is the even weirder idea about the origin of life. The idea here is that life somehow migrated here from somewhere else. Now, again, that might sound totally crazy, right? And in fact, there's even other people that talk about natural panspermia. In other words, something that happened by accident. In other words, let's say you had a life form on some other planet, and somehow it hitched a ride by accident, basically, onto a meteor or something like that, and it hit us, and then it thrived here. The other talk is about directed panspermia. So this would be some being decided to send life forms here. This one right here I think is a little bit weirder, of course, but we're still not sure, obviously, which one is which. But I think it's really important to know about which things we're talking about here. I want you to be well educated and well informed so you can talk intelligently about this and have your own opinions. Now, How could something actually migrate? This is totally crazy sounding. We're not necessarily expecting spaceships coming in, although I suppose it could have happened, but we're not necessarily expecting that. So we're going to talk more about sort of natural forces here. Now, we're going to talk about a little bit of nomenclature here, so a little bit of terms here. We have things called meteoroids. You might have seen this as a word. You might have heard the word meteor. And you might have heard the word meteorite. And you might think, what is the difference? Because these are commonly used, and yet you might wonder what they are. So a meteoroid is just when it's in space. So this is some object. This could be a comet, it could be a piece of rock, it could be whatever, it doesn't matter. Some object in space, usually rocky. While it's in space, we call it a meteoroid. It could be really big, we call it an asteroid, and that's a little bit sort of fuzzy definitions. But basically, we're talking about some space rock that's coming into Earth. Meteor is while it's in our atmosphere. So in other words, right here, for example, in this picture, on this diagram here, we're showing one that's probably burning up into our atmosphere. This is what we would call a shooting star. We would say that's a meteor. Now, why does it get so bright like this? That's because we have our own atmosphere, which is above the Earth here. And the atmosphere is fairly thick. It's got all these nice gases that we like to breathe. Well, it turns out that those gases are fairly thick, which means something coming in really fast is going to heat up through a process we call friction. And you understand friction very well. I mean, just rub both hands together, just back and forth really fast, and you'll feel that there's heat generated. Well, imagine that on a very large scale, a very extreme scale, and that's why these things sort of burn up in the sky. And that's why a shooting star looks so beautiful, right? That's just because it's entering our atmosphere. So this thing which was in space, as it comes into our atmosphere, it looks really bright, so we call it a meteor. And then after that, of course, maybe a piece of it actually lands on Earth. So maybe it actually lands. So we could say on land. So if it actually did manage to make it onto land, because not all of them do. A lot of them are just little pieces of sand, basically. And a little piece of sand or dust is probably not going to be found on Earth here. In fact, it may just vaporize completely. But sometimes we can actually find them on the ground. I think that's what's really interesting. So we might be wondering, well, how can this all happen?